So I think I get to go first because I'm a little bit of an outsider with computational social science. And I also told them they could be as mean as they wanted to me to be an exemplar about not going over time. I agreed. So I study collective behaviors in complex systems. So I do a lot of mathematics, applied math, physics modeling, and study things like phase transitions, pattern formation, self-organizing cascading behaviors in systems with millions of degrees of freedom, the thermodynamic limit, and also looking at asymptotic properties. So I make mathematical models of infinite-sized systems in their steady state and study things like their phase transitions and collective behaviors. So today I'm going to talk about a small subset that I'm familiar with, mathematical modeling of social behavior. So there's tremendous history in analyzing the extent of epidemic spreading or product adoption, and lots of different kinds of mathematical models that we can develop, all based on understanding what are the mechanisms that would make an individual change his mind. And these are really well-known famous models like the threshold model, voter model, opinion dynamics, percolation theory, game theory. So those are the tools that we use. Here's a nice graphic from an article we wrote showing the impact of zealots, and I'll get back to that in a second. So even when we ask this question, what are the mechanisms that make an individual change his mind, we have to go to a very simple frame. So even if we think about the most basic model, what makes someone change their mind? Is it a diminishing return that every subsequent friend makes me more likely to adopt a behavior, but the first friend had the most influence? Or is there a threshold, a sharp threshold? Once a critical mass of my friends adopt a behavior, I adopt it. And it leads to very different kinds of results, very different phase transition locations. Another very famous model, the voter model, is basically the tell me what to think model. So I choose a neighbor at random and I copy their opinion. And if I'm going to be doing that all the time, if I have a power law degree distribution, a broad scale degree distribution and connectivity like we see typically in social networks, then it's the high degree nodes that dominate their opinion, because with high probability, most nodes are very low degree, so they copy a random neighbor, and that random neighbor happens to be a hub. So in the voter model, tell me what to think, the hubs end up dominating. We can think of the opposite model, which is called invasion percolation, and that's kind of the bully model, because I choose a neighbor and I say, you have to listen to my opinion. And in that case, it's the leaves that dominate. So again, totally different phenomena. Another model that I've studied a lot is the naming game, which is a little bit more meant to reflect consensus amongst people, that you can have multiple opinions and that you talk with your neighbors until you all reach consensus. And in this very interesting model, there is a great role of the impact of zealots. So if you have a few committed minorities who will never change their mind whatsoever, it can have dramatic impact on the process. And on that voter model, the tell me what to think model, a finite number of zealots sways the outcome. In the naming game, a finite fraction of zealots sways the outcome. So you can see why that's so radically different. In the first case, we just need one or two individuals in order to change the outcome of an election. In the second case, we need 1% of our population to be zealots before they can have large-scale impact. And then we've also studied things with having multiple choices and show that it can lead to very different kinds of collapse or product adoption behaviors. So in general, we've been studying phase transitions in collective systems, and we look a lot at these kinds of smooth transitions, which tell us about epidemic spreading, product adoption. There's also these great kinds of abrupt transitions where we see some behavior last for quite some point in time, but then abruptly switch to another behavior. And that's modeled by a classic third-order differential equation, makes a beautiful phase portrait, and it models things like product adoption. So you can think about the blue line being everybody listening to vinyl records, and once we reach a point that internet penetration is so high, everybody jumps to digital music. So we used this model together with George Barnett and Charlie Brumet, a really bright student who finished his PhD here about 2 years ago. And we used this idea of these cusp bifurcations. And we said, what if we couple two systems together? So we know that product adoption in one country can drive product adoption in other countries, or things like ecosystems drive change in adjacent ecosystems. So we looked at this model, and we coupled three systems that each individually go through this cusp bifurcation. And we found an interesting phenomena called catastrophe hopping. So we found that the first system could topple and go from one branch of its equilibrium to the second. It impacted the system that depended on it. That's my timer. It impacted a system that depended on it, but the system didn't topple, but it weakened enough that downstream dependencies did topple. And then we looked at the Arab Spring data, and we found a lot of those motifs there, that the periphery is disadvantaged by the core. And this is something that we put together at Proceedings of IEEE about how the online world is really changing the game, that we're gone from localized power to massive amounts of information in our digital footprints. Whoops. I'm getting ready for the next person. And so this is my take on why I'm here, because we've done all these math models, and now we're in position to start pushing those models with real-world data.
As a guest of the Computational Communication Research Center here, I'd like to focus on computational communication research, CCR for brief. CCR is a small subset of CSS. There are a lot of chronos here. We primarily focus on a narrower set of computational methods, including user analytics, content or text mining, and online experiment. And these methods mapped nicely to the traditional social science methods such as survey, content analysis, and experiment. And they are also closely related to the primary focus of communication research. For example, user research, content research, and effects research. Now, what I have brought to the conference is a small-scale content analysis of what have we done, what have we learned through this computational communication research. And we have collected data and also performed some preliminary analysis, all using, strangely enough, old-fashioned methods, manual coding instead of machine learning, because the kind of things we try to get an answer to it is very challenging, even for human judgment. And we went to the Web of Science collection of communication journals. There are more than 70 journals. So we identify 1,200 articles on social media, which is where we believe computational methods are concentrated and more frequently used. And then we went through manual coding of those articles and identify about 16% of the articles, 200, to employ any of the computation methods we just identified. So that leads to a first conclusion that computational methods have been relatively a lightweight player in communication research. And of course, over the years, computational methods have gained significant visibility in the field, especially in the last 2 years. The percentage rose from about 15% to more than 25%. And we believe this is going to be a trend to watch in the next few years. Beyond quantity, we are more concerned about the quality of computational communication research. And obviously, the question of how to assess the quality of research is a challenge for any field of scientific research, especially for social sciences. And we try to focus on the amount of knowledge that any of the studies we evaluated created on top of what have we already known, nicely fitting the theme of the day. So we believe that if a study merely confirms what have we already known, we consider this as a new bottle of old wine as a mere confirmation. If a study brings us some new phenomena or new mechanism, and then we consider it as a new. And perhaps this is a very early stage result that we found about 80% of the 200 studies have been largely just a confirmation of existing knowledge, with the remaining 20% contributed to our knowledge in some ways. Some provides description of entirely new phenomena. Others offer some theoretical hypothesis to some phenomena that we have already known. A few, about 3%, 6 articles fell into the most ideal situation that provides new evidence, and also on top of that, some new theoretical framework for that. That's the overall finding from our little study. We'll be going to release more additional findings in the coming ISA conference and through other venues. Thank you very much.
I'm going to speed through the slides that I have here. I want to first ask the question. So the title of the talk is, can CSS remotivate new theories, data sources, and methods? I want to do a much more high-level picture. I'm not talking about specific research that I have conducted, nor am I doing a great analysis like Jonathan has done of other people's research, et cetera. I'm going to argue that one of the things that we can think about is that CSS, it actually fits really well with what Jonathan just said, whether we're looking at new phenomena, looking at new theories. And so this is an example of how sometimes you can have a situation where theories have not been able to test at scale, such as things like brokerage and mobility, that we are now able to do. This is an article that just came out that Sinan and his colleagues worked on in terms of looking at contagion and behavior change based on the networks. Other examples of similar things are things that theories that focus attention on new or at least increasingly prevalent phenomena, very similar to what Jonathan talked about, the new phenomena, et cetera. This is an article, again, by Dirk Helbing and his group that looks at optimal incentives for collective intelligence, which is a relatively new area that is coming into play here, et cetera. We can also look at theories that invite consideration of new combinations of variables. This is an article that Emily Falk and her colleagues look at, where they combine social network data with brain networks, which is a nice, interesting way of combining different types of variables, which we have not combined together in the past because it was not possible to do that. So one of the exciting things here is to see different ways in which computational science is helping us extend theories in different venues in different contexts. Obviously, we have lots of different kinds of data sources that we now can celebrate and look at, and this was a work that Cindy and others worked on called the Virtual World Exploratorium, where along with our colleagues at USC and at Illinois and Minnesota, we built up a really large corpus of data on online games and used that as a way of studying these things. One of the cautionary notes to remember there is that sometimes we look at data because it's available, and sometimes that may not be only the right data to look at. This is the case of the drunken guy who was looking for his keys for his lost keys for his car under the lamppost, and when asked why, he said because that's where the lamp is. My colleague Scott Poole says that not only do we do this with data, but sometimes, unfortunately, we also do it with theory, where we take theories that exist and then try to force feed them into what we are doing. And so we need to be careful on both of those issues. Obviously, we have several new measures of collecting data, sociometric badges. We can get data from sensors, human activity. This is work that Sandy Pentland's group has done on looking at the science of building great teams by looking at sociometric data. We also have crowdsourcing data that can be used where we collect data from places like Mechanical Turk, which provides us a much more diverse data sample than all the previous psychological studies that were done largely on undergraduate students at large Midwestern universities, not very generalizable. We also talk about crowdsourcing data from people intentionally. David Lazar, who was the lead author on that Science magazine article that we wrote, has created a platform called Volunteer Science that many of us have been involved in, which allows people to go in there and collect data. We can sometimes also look at it unintentionally. My former colleague Dirk Brockman at Illinois looked at data from Where's George, which was a website playfully created to track George Washington dollar bills, etc. But he actually used that, and as you can see at the bottom in the New York Times, he was able to use a network of mobility patterns amongst people based on where these George notes went, and he was able to predict the flu with the aid of George Washington. We also have to realize that there is big data in the laboratory, and that even a lot of the work that we do in the lab, even though it's a small amount of people and for a short duration of time, can generate lots and lots of data, whether it's server-side data, whether it's chat data, text data. This is an article that my colleagues and I wrote on titled Little Teams, Big Data Providing New Opportunity for Teams Theory. More importantly, I think we really have to make the move from big data to data fusion. My colleague Jim Hendler, who's at RPI, says the era of big data is so 2012. Enter the era of broad data, which is really the juxtaposition of diverse forms of data that we can use in this case. In addition to data sources, and finally, in terms of methods, we have lots of interesting ways of looking at confirmatory methods now for this, having new focus on things like relational event models and networks that look at timestamp data because it's available and we're able to use it. My colleagues and I have done some work on developing these models and applying it to the study of team interactions. We also have computational methods, which we'll hear more about, obviously, et cetera. But here again, we have taken a situation where my team has developed models of what would be the positive affect and negative affect relationships amongst crews going to Mars, the mission of Mars. And this is research that's funded by NASA that looks at how we might want to look at these dynamics. Another important issue is to combine theory-driven and data-driven approaches. In social sciences and communication, along with that, we have focused primarily on the hypothetic deductive logic and have been very wary of exploratory mechanism. But now we have ways of looking at machine translation and mining text for social theory. This is work done by James Evans, et cetera. In closing here, the last slide I have is looking at methods, and I think one of the important things is we tend to think about hypotheses. I couldn't resist having a bottle of a wine that was labeled hypothesis on the left, but now we want to think on the right of having not only hypotheses, but thinking of hypotheses that are like Boolean logic statements that come out of machine learning and using that as another way to think about hypotheses. Thank you.
Stand here. I always have to follow a great speaker. Thank you, Nosh. What I wanted to do today is begin with talking about what I do. For those of you who don't know me, I look at international communication networks, and I've been doing this for a really long time. These are among the different international networks that I've been looking at. One international network that I've been looking at a lot to show you that people have been doing big data for a really long time, is the International Hyperlink Network. And we began doing this in the late 90s when we only had 90 million hyperlinks. The second study that we did using a Python script to gather the data, we had 356 million hyperlinks. In 2009, when we replicated that with data from Alta Vista, we had 9 billion. In 2010, we had 14 billion. This is pretty much what the network looks like. The size of the node is the number of received links. The big yellow one is the United States and Canada, and then you have Germany, Japan, and so on. More recently, I've been measuring international relations through social media conversations. In particular, what I examined were Facebook and Weibo posts in order to examine international, transnational forums. And there's all a bunch of theories that we could use to talk about it. But to obtain diverse political orientations, cultures, language, interests, geographies, and collective identities. And the question we were really asking, what are the relationships among countries as expressed in the social media of people's postings? And the data, we used 200 country names. We used the Google search with a paid API for Google. And it was a simple query that is the number of hits, country names from Facebook using United Kingdom and America, how often were they co-occurred. We replicated this in Google Hong Kong in Chinese for Weibo. Because Google only allowed us 10,000 searches a day, it took us about 3 weeks to gather the data for both data sets. And we got 1.8 billion posts from Facebook, 51 million posts from Weibo. We took all the synonyms that were used for the United States and UK and combined them into one. And basically, using Gephi, this is what the network looked like. To no one's surprise, the United States is at the center, and it really does look like what world systems theory would argue, with the core countries that, being more tightly connected and the more peripheral countries being smaller and so on. People don't talk to them. In Weibo, the center was Hong Kong. To no one's surprise, perhaps because we gathered the data in Hong Kong, but perhaps because this was with the democracy movement, the umbrella movement in Hong Kong during the time that we gathered the data. And the strongest relationship, obviously, is China and Hong Kong with the United States, and otherwise looking at it from a world systems perspective, but with an Asian bias. That being said, the biggest problem I see facing the future of computational social sciences is that currently social science students do not have the required skills to become computational social scientists. As a result, few social science students are qualified or interested in computational social sciences. We need to change the curriculum. We need to make it STEM. This is what a typical STEM curriculum looked like when I was an assistant professor at RPI 40 years ago, where all students had to have a couple years of calculus, differential equations, linear algebra, had to have 2 semesters of physics, 2 semesters of chemistry, 2 semesters of biology, and with that, we could throw in some computer science and the social sciences. Let the students have their choices. Then they can major in social science, not social studies. Students with this, will have a STEM background, and they can always go on. I guess I'm done. There are advantages, and okay, but I'll also say in the graduate curriculum, we should allow students to get credit for courses in math, computer science, and the natural sciences. And there are a whole bunch of implications for this. Thank you.
Okay, I'm a computer scientist, so I might be coming from a different perspective. So similar to what George you have done, that we're basically trying to analyze the online activity, and we try to provide a social interpretation about what's going on over there in our world. So for example, from the data set perspective, about 2015, there was a study saying that, well, how many public Facebook page were there? It's about 50 million in 2015. So we actually developed a crawler, and until right now, we probably have about 52 million Facebook page. So which means that we actually be able to kind of capture a very complete picture. If it's not 100%, is approaching that, and we're still doing that. And then what we do is that, this is something, George, I should really talk to you, is that we found 50% of the page, they did not declare their country. So we developed algorithm, and now we will be able to, with 93% accuracy, we'll be able to plot their country. And then we actually show that picture, which is similar to yours. But one of the study we actually found out, among those public page, they actually split. One is a US, Canada, UK, Australia. They form the hub and then connect everybody. The other part is essentially Muslim world. Yeah, and that's the separation over there. So we look at all this data. What we want to see is that we want to apply the social science principle to help us to provide that social interpretation. And sometimes it works really well. Sometimes we have to twist. But also, as I think mentioned by a former speaker, that also, we actually found out we might need to have a new social science principle to help us to deal with that situation. I mean, some of the applications I want to tell you what we have been doing. For example, we're looking at attack, that people sharing malicious content in comments in public discussion. And we're interested in why this attacker is interested in sending this particular content at this stage of discussion. And the thing is, that's how we model, and then we try to come up with a model to understand that. But also, we, just for example, that we leverage one of the results from communication information cascade, and we found out that that matched really well regarding how they decide that's the right point. But this is also related to how Facebook delivered. This is one topic which I will emphasize. It's called system artifact, which is how does the system artifact, such as a network service or Facebook, their selection of information, and such that people receive different kind of information in different time. And you have, in fact, today, you have a very small time window, a few minutes, for you to react to some of the content. And that is very different from some of the principles that we can apply here. So we also apply to issues such as fake news, is that, well, are there ways that we can computationally identify certain pattern from the data that somebody tried to divert the discussion and try to alter the consensus within certain pages, and why and when they do that? So let me actually, before I talk to my most interesting example, I want to just first tell you that summarize what I talk about in the first slide is essentially we look at different things. We look at per user behavior. We look at a group of users, because sometimes a group of users, they share one single account. And we look at a more long-term properties, such as a social structure, about how social topology is there for this particular group and that particular group, and how they interact. But the thing is, that is a more, I have only 1 minute. Okay, so social interaction, real time, but I really focus on system artifact, which I want to, this is just the size of the data we have today. So now this is in the past 6 months, I've been focused on Syria. So Syria is interesting. There is about, 200,000 pages within Syria related to Syria they were discussed. And the people participate. There are some of the people in Syria, some of the people in Turkey, Russian, surrounding area, and a lot of community. In fact, one of the community in Sacramento, they actually interact and with different timestamp, and they talk about that. So number one, we're saying that, okay, this is an incident. This is what I call one example of system artifact. The Syria Electronic Army, they shut down their internet around the border. Before the revolution, they tried to do that. They shut down for 24 hours. So just show you one of the slide down there. Each dot over there is represent a activity in timestamp. So the y-axis is 0 to 24. And then that was a few months around that shutdown. So you can see that there's a clear shutdown over there in the red circle in here. So basically, of course, we can recognize that. But what does that to do with a social interaction? And that's actually very interesting phenomena. And also, if you look at the one on the top, okay, I have to say this. This one, you see there is a block of empty time. That's a sleep time. And sleep time told me a lot of information. This person is in which time zone? This person is in Syria area or in US. That is very important. Number two, it tells me this is a real person or not. Look at that account on the right top corner. That was, we believe, that is an electronic army. So you can see that is everywhere. If you look at the content they're sharing, that's even more interesting. Of course, it's Arabic language. And so that's kind of present a bridge between computer science, which we understand the system who deliver the information, the system provide the network, and the social interaction that's actually social science has been studied. And I think that's a new area for us to understand both the system perspective, because we rely on that so much. I better get down. Somebody already said that.
It was opened somewhere. It was closed. Here you go. Here you go. Now it's running. Okay, I have used up 2 minutes. Okay, thanks for inviting me to participate in this panel. I'm from Michigan State University. I'm Winson Peng, and we did a study to review to map the landscape of internet research in 2013, and we mined about 30,000 internet studies published in mainstream social science journals. And we find some research themes in internet research, and also we look at the methods used in new media internet research. And we found that quantitative research methods actually is the dominant method, but out of the quantitative research methods, the traditional methods is still take the large share of all the published studies. And the computational methods at that time, mainly the behavioral log analysis, only account for a small proportion of the published studies. And since 2009, and when the Science published the manifesto for computational social science, and the picture seems a bit different. Everybody is talking about big data, everybody is talking about computation. And a lot of researchers will put the equal sign between computation and big data. But what I want to say is that computation is not just about the data size. And there are a lot of pitfalls or some perils embedded in this kind of very big data sets. We have this kind of noisy, we have a lot of missing values, we have a lot of fake or robot accounts, and we have some big and non-representative sample in big data. And to me, or to some of the research, I think when communication meets computation, it represents a kind of paradigm shift. We shift from traditional thinking paradigm to a kind of computational thinking. So what I want to remind us, including myself, is that it's a kind of computational thinking. What is computational thinking? It's beyond the scope of today's talk. And Janet Wing from Carnegie Mellon, and now she is a professor at the Columbia University, and she published this study in 2006, I think, and he argued that computing is the abstraction, is the automation of our abstraction. Abstraction is kind of identify the research questions, and then you make it to a very higher abstract level to express everything that computer can understand and can implement automatically. And to me, I agree with Gary King's argument in one of his, actually it's just a very short essay, and he argued that computational research is a kind of tripartite integration of three components. The first component is the well-articulated theoretical model, and the second part is the innovative statistical methods, and the third part is the novel computational algorithms. So where is our series from? And this is the theoretical relationship we mined from internet research in 2014. And we found that in internet research, psychology, business, information science, and the economics and the communication, they are the major theoretical source, while sociology only plays a very, very minor role in the early stage of internet research. I'm not sure whether the picture will be revolutionized with the popularity of the computational social science, but this can provide us some hint to understand how our computational communication research is now looking alike. And with regards to the methods, now everybody is talking about computational methods, but what can be considered as the computational methods? And this is my summary. I think it's a kind of ST square. We use social network analysis, we use text mining, and we use the spatial modeling, and we use the temporal modeling to handle different kinds of data available, either from online sources or from offline sources. But when we embrace this kind of new methods, new algorithms, to me, we need to sing our old songs in traditional social scientific research. The first old song is the unit of analysis. We now have the luxury to design our research at different levels of unit, but the Simpson's paradox or ecological fallacy become a more prominent issue. So we need to think about the unit of analysis very carefully when we do computational social science. And second, measurement error is everywhere. It's still there, even we have this kind of user-initiated digital footprints on social media. Measurement error is still there. And third, as the Nash has mentioned, data fusion is very important. And now most of the computational studies focus on one single platform and focus on one single behavior. And we need to put our human beings back to more complicated but more realistic social context to understand their behavior. And we need to unravel those complex relations and to examine higher level, higher order interaction across multiple mechanisms. And also what I want to say is visualization is very important, not just to present our findings. It can help us to uncover some hidden phenomenon or mechanism buried in very noisy data from online and offline sources. And this is a very hot debate in psychological field, and I think our field, computational field or communication field, needs to think about the replication and the reproducibility issue very seriously. And finally, to recompute the social science, I think we need to open our mind and to meld knowledge from existing knowledge and the future knowledge or the emerging knowledge, and melding theory, algorithms, statistical methods together. So that's my presentation. Thank you.
Wow, I'm deeply impressed. Really, we are doing fantastic time-wise as well, and I think inside-wise, I'm really impressed. Until now, my prize goes to Nash. Did you guys notice that was 24 slides in less than 5 minutes? So that was 12 seconds. Every 12 seconds, a new slide. So I'm learning here from the masters. When I put these slides together this morning at 6 a.m., I thought, like, no way he can go through 24 slides, and he did actually. He finished before the 5 minutes. I paid attention. That was put my head for that. Right. Good. All right. Okay, my 5 minutes. For me, the problem is stationarity, which is our best friend, because only if a process is stationary we can actually say something about it, and it is our worst enemy, because especially in the social sciences it messes everything up, because social systems are not stationary, and we don't want them to be stationary. So I want to talk about that. So if you have a statistical dynamic that looks something like this, there's nothing in the data that allows you to say that this dynamic would change and would be different. Like if you do empirical data, big data, small data, whatever data, the future has to look exactly like the past. Now, in social science, we don't want the future to look like the past, right? You want to have a better world. You want to have a world without poverty, without pollution, without wars. But we don't have data on that. Absolutely, we do not have data on that. And then actually make things worse, the economists they call it the Lucas, a Nobel Prize winning, the Lucas critique. So what we do is we study our data, then we do design policy interventions, private, public sector, whatsoever. With that, we change the very dynamic that produced this data, and then we happen to say, oh, now the future's, and we have no idea how this future's going to look, because per definition, we just destroyed stationarity by acting on the world, right? So that's a very severe limitation. Okay, so let's see what the big data shows us. So I'm in a communication department, so the biggest communication processes I can think of, for example, is in Wikipedia, and the most edited site in Wikipedia is the site of George W. Bush with 46,000 edits. And what I did here is I derived the epsilon machine. So that's the smallest size, optimal presentation of this data series with a maximal predictive capacity of it. So that's it's actually cool that in the social science we can now do these kind of things, right? So that was developed for physics, and now, wow, we can do something. That's basically, it represents the Kolmogorov complexity of the process, the best approximation of it. So that's an amazing thing that we can do things like that. But if I now compare the first half and the second half, the process looks quite different, right? During the first presidency of George W. Bush, there was a different process at hand, so that's basically a hidden Markov model, than in the second half. So something else happened. So maybe we need bigger data. So then the biggest data that I actually found is the communication process behind the creation of Linux. So these are 600,000 communicational turns. and I calculate the epsilon machine, which is a little bit more complex, with 25 different states. And if I divide the first half and the second half, well, it's smaller. That means that there must be states in the first half that are not in the, or that are not in the total. And if I go by quarters, again, I get in the first quarter a hidden Markov model with 11 states, then much more complex in the second quarter, 16 states, 15, 18. So actually what's going on? So the thing is constantly changing. Right, so I can actually, making a statistics, what am I talking about here? I can even then, I pieced it even further apart and wanted to know how much of the structure in this dynamic communication process comes from static frequencies. That means that's all of our friends who calculate variances, right, a static frequency, and how much from the dynamic. So I calculate the entropy rate, so how much comes from the dynamic, and I pieced it apart. By the way, 3/4 come from static, so that's good for all of us who like variances. Only 1/4 you can get out of dynamics, but that quarter is important. Now, if I piece it apart with regard to stationarity, what you see here is that actually stationarity affects static and dynamic frequencies very differently, and it affects it. Actually, it makes static frequencies much more reliable, and actually it makes dynamic frequency less reliable, which is interesting. So more stationarity, less predictability out of dynamics, which is a funny thing. And actually I did that here. So I have a level of stationarity because I gave up on defining something stationary. So what I did here, to explain, I took the 600,000 edits from Linux, I divided it up into 2,000 groups, and I ran 3 million chi-square tests among all the combinatorics. And then I calculate a level of stationary, because social dynamics are not stationary at all. Now, we have the ambition to become a science, and we say like, oh, we have 80% predictability, 90% predictive accuracy, like in the physics, but physics systems are stationary. Ours are not, and we don't want them to be stationary. We want the world to be a better place, right? So it's a very funny thing, and I think that's one of the lessons learned, I think, of the first decade of the computational social science. Of course, then when we become theoretical, and in the third panel, so the next panel we will talk about big data, and in the third panel we will talk about computer simulations as well a little bit. Yeah, in theory I can use computational social science as well to create futures where I do not have data about, and I can simulate non-stationarities, but that is not grounded in ground truth. These are just, theoretical constructs, imagining a better world, right? And now you go to a policymaker. So I worked in the United Nations for 15 years. You go to a policymaker with kind of like a SimCity model. They will not pay attention to you, really, right? It's like, oh yeah, he played with SimCity, and what we have to do is like, no, So there's a big challenge there, and I think so. Yeah, and I'm saying I think our best friend and our worst enemy in that sense is stationarity, especially for the social science, and I have no idea how to deal with it. All right, thank you very much. So maybe we ask all the panelists up here. We still have 15 minutes. So we still have 15 minutes, and if any question came up now, for anybody that we cut brutally short here, feel free to ask the question. If not, also from the panelists, if somebody has another reflection that now came up and that we didn't allow you to get to, feel free to use that now.
Just ask that everyone speaks into a microphone so that we can pick it all up, including questions.
Okay, so I'm part of the organizing committee, so I get to ask a hard question. Some of you mentioned, and I think especially Felix, about the role of computer scientists, and I think Nosh mentioned as well that the difference between theory-driven versus data-driven approaches. So as a social scientist, nowadays I often see that computer scientists are taking their very fancy algorithms and computing power to look at some of the social problems we think that wants to be our turf. Okay, so as a field, I feel that we are sort of cannibalized by this outside force that's very strong and using their very fancy algorithm and such and studying social problems. But as I understand, the role of computer scientists or the purpose of their research is mostly about prediction. How do I improve my predicting algorithms, to the best accuracy possible? Where social scientists tend to have this purpose of trying to understand social phenomena, so we could, make some prescriptive changes and such. So I was thinking, if we are going to join forces, and we are going to use some data-driven approaches, while computer scientists are trying to team up with social scientists to understand the phenomena much better. Can you offer some thoughts on how could we make that approach possible? How could we better join forces from the social side and the computing side?
All right, okay. Oh, I have to hold it. Okay. I'm sorry. You see that how good I am as a technology person. Okay, that's good. Yeah. So, in fact, I was invited to give a talk in the Social Science College in National Taiwan University not long ago. So the talk, by the way, is still online. Basically, my message is that I'm a computer scientist, but I kind of see this a little bit different from most of the other computer scientists. I feel social science should take the driver's seat. To me, computer science, we're just providing tool. And the tool, we're going to develop all kinds of tool. But while George was saying that, well, social science student doesn't have enough stamp, and I feel computer science student is very skin deep in terms of their understanding about human. I feel computer scientists really need to understand, develop more interest into humanity and social science, and then they can actually start to have the same vocabulary, the same passion to work with social scientists. I feel that computer science can contribute when as you said, predictability is one issue, but computer science usually, if social science already solve all the problem, they model together. At some point, computational thinking, I thought is Jonathan mentioned that, is that at some point, computer science just throw in their tool. But I feel that the first stage about developing what is the most interesting things to, I say I'm different from computer scientists. When I start this project, my first statement is let's kill Google. Because you can see today, Google, Facebook, how they impact our life. And the thing is that a lot of computer scientists, when they start their career, they're thinking about how to join that area, which is, that is a little bit dangerous from my perspective. So I hope I answer some of your questions. But I'm looking forward to collaborate with social scientists, and I feel you guys should take the driver's seat.
I want to add some to Felix's comments. I don't want to consider computer scientists as a kind of tools provider. Yeah, when I work with computer scientists and when they design any system, any algorithms, their original intent is to understand human beings. So they can provide some tools that can be utilized by human beings. So I think from my experience is that they like social theories. They like this kind of very creative social theory that can work with them very well and that can help them optimize their system, their algorithms. So when we submit something to computer science journals, the reviewer or the editor will say, hey, this is a very good study developed on social theories. This is one of the major contributions of the study. So we are equal collaborators. We should work, I like the term is seamlessly. We cannot just say, hey, computer science is just a kind of tool provider. Yeah.
I think that those are all really good points. To me, I see, having had the opportunity now to work with a lot of folks, not just in computer science, but in other branches of engineering as well, I think that the real value add is when we can work on a project that pushes the envelope in all of the different areas. So when I work with somebody in computer science, I'm always wanting to make sure that they are also seeing the problem that we're addressing as not just helping to answer a social science question, but potentially to also push the boundaries in computer science in terms of algorithms, in terms of techniques that they're building, et cetera. And so those kinds of projects, I think, are the most win-win projects, and that's the case where I feel that when we have to educate our students in the social sciences, that they have to learn enough about what is happening in the computer science realm to be very informed consumers of it so that they can engage with it. They understand what it means to look at the results of machine learning, what it means to how to interpret things like precision recall and F ratios and ROCs and AOCs, et cetera. So that is something they're never going to be experts at. I don't think our students need to reinvent those kinds of techniques, but we need to be very informed consumers and partners and collaborators with people who are working in that area.
Let me just add, if I would have gotten to the implications section, that probably the most important implication is getting social scientists and the STEM sciences to communicate better and having the ability to speak a common language, and with that common language, getting the that we would be able to facilitate all the things that Noshir is talking about, all the things that Felix is talking about, all the things that Winson is talking about. And I think it's really important that we get back to what I would consider a traditional liberal arts education, where the math and science are really an essential component of an undergraduate education.
This line of conversation reminds me of a very interesting encounter that I had about 2 years ago when I was invited to give a talk at a national conference on social computing, which is a term equivalent to computational social science, but mostly popular among computer scientists. And my talk was on how to collaborate between computer scientists and social scientists, and I tried to get a message over that as a social scientist, we should not overestimate the ability for computer scientists to solve social problems. And the chair of that panel, a very distinguished scholar in physics and also complex networks, responded with a very, very interesting turn, because he has worked very extensively with several social scientists in different disciplines. So then he offered also the opposite side of the conversation, that as computer scientists or scientists in general, never underestimate the ability of social scientists. And this pair of conversation was very, very central to the conversation we had. But from my experience, there are a couple of hurdles for social scientists, especially for those of us who have been doing computational work. One of the things is that quite often for scientists, especially those who are interested in studying social media, social networks, they equate social sciences to sociology. So whenever they have a problem, whenever they need to look for a collaborator, they go to their department of sociology. And most of the time they found that sociologists are not interested in social networks, even though traditional social network analysis originated from sociology. And so that's a challenge for us. So we need to educate, or we need to promote that there are many other disciplines inside social sciences that are interested in social networks. The other thing is that well, I lost my thought, and I'll come back to it.
So I had a question. You folks have been talking somewhat at the technical level of the intersection and the nexus between social science and computer science. I'm a PhD student in a social science domain, and I definitely agree with that sense of the maybe lack of training to make those connections happen, at least to date. But could you weigh in on how these different approaches actually shape the theory, because that's another drive of the need to integrate theory. But I, in my experience, have found that the tools that we use to develop theory bound and shape them. And so what do these new approaches add to social science theory? Does it change it? What does that look like in your opinion?
I'll go. Okay. I think that's a very good question, and I'm glad that you asked that question, because I think one of the important challenges we in all of the social sciences have to recognize is that to what extent are we using it, as we said, to sort of reinforce existing theory. One of the interesting things, so there's a long tradition of what is referred to as methodological determinism, that the methods you use shape the questions you asked. That when people were trained on doing crosstabs, the world was all about 2x2s, and when people learned about ANOVAs, that's what they used. Same thing with regression, with structural equation model, with time series analysis. So we see that. So what is new about computational social science now is that if you're looking at techniques like machine learning, for example, since we'll just take that as an example, and you're looking at ways in which you're able to start look at, say, decision tree algorithms. Okay, so now all of a sudden you're getting predictions that say if A is between 1 and 6, and B is above this much, or X is between so and so, then you have a 98% chance of being able to see a particular phenomena. That's a very different way of theorizing that we traditionally have not done in the social sciences. And so one of the things that allows us to do is to think about a new vocabulary, a new language, a new structure of making knowledge claims, which actually fits very well with systems theory in terms of principle of equifinality, which says there are different ways in which you can explain a particular outcome, and our traditional approaches talk about a single way to get to that particular outcome. So I think that that's an example of how just talking the language of machine learning is now making you think differently about theorizing about questions. The second one, I think, is that when you start juxtaposing very different kinds of data, you've not theorized about it because you never thought that it's possible that there are physiological underpinnings in your brain network, for the example that I was giving with for Sandra's colleague, Emily's research, and looking at that along with social networks. So I think that those are really important things. I have one thing to add to Jonathan's comment, and maybe it'll jog back his own memory of the point he was going to make. Now I've had the opportunity for 3 years now to be involved in organizing of these international conferences on computational social science. And one of the interesting conversations that I often have with some of my less enlightened non-social science friends is when we have to put together speaker lists of who would be the keynote speakers. And they go, yeah, we should make sure that we have an even split between computer science and social science. And my colleagues Duncan and Brian and myself go, there's a little problem with that because the social science is an umbrella term that talks about a lot of social sciences. So when you don't want to talk about parity, you say, yes, we can have parity between physicists and computer scientists and sociologists and psychologists and economists. And all of a sudden, he's like, oh, wow, so you don't want to consider those as just one bucket? No, not really.
Yeah.
Just to follow up on that about how it's changing our theories. So, doing mathematical modeling, we always are trying to think of simple mechanisms that give rise to these collective phenomena, and we kind of make things up. And typically because we can analyze them, threshold models, smooth curves, but it's really amazing that the digital footprint is revealing the way people really work, really think, what really drives them. So it gives us the opportunity to come up with new theories because we can observe behaviors and try and think of what the underlying mechanisms are. So I think it actually is a great opportunity to push theory to new places that are going to be more accurate.
Yeah. Let me just add one little point, is that in the natural sciences, STEM sciences, they emphasize the notion of discovery. In the social sciences, we've been hung up on this logical deductive model of hypothesis testing and building theory that way. And I think that what will be happening as a function of the computational social sciences and the merger of the STEM sciences and the social sciences, that there'll be a more emphasis on discovery and more inductive theory construction.
All right, so I had a question that that relates to a few of the comments that a few of the panelists have made about disciplines. So to my mind, computational social science, one of the big novelties about computational social science is that it challenges all traditional disciplinary boundaries, right? So sometimes I think that I have more in common with colleagues like Raissa than with some sociologists. I'm a sociologist by training. And so what matters is the questions that drive our imaginations and interests and how we're going to answer those questions. A couple of the presentations and also comments in the panel, sort of, what does it matter that sociologists are not the only ones who are interested in networks? So in a way, I guess what I'm asking is that this institutional representation of knowledge compartmentalized in disciplines, and this is, to a great extent, it's a historical contingency. Knowledge is unbounded, right? But we have to compartmentalize things so that we have universities and departments. CSS is challenging a lot of those boundaries, I think, and so there's a bunch of new research institutes that are coming up that are at this intersection, and they don't have a clear identity. So in terms of which discipline is the home discipline. So I guess my question is, why does it matter whether we are sociologists, physicists, or engineers, if what matters is the answers we can give to questions related to the theory, right? So ultimately, theory progresses when we can provide better answers to all questions. And so what are your thoughts about that? Why do we still care? And I'm in a tenure track position. I do care about discipline. You still need to abide by. But why do we care so much about the labels we attach to ourselves in terms of disciplines, right? Isn't that contradicting the spirit of CSS?
Actually, so this sort of, I want you guys to answer this, but this is sort of like a follow-up question, and it also relates to the first question, which is that I think I've been to several events with similar conversations, and it still seems most people are pushing the paradigm of collaboration between, an expert computer scientist and an expert social scientist, and certainly if you look at NSF solicitations, they're all about these collaborative undertakings. And there is another model, which is and this might feed into discussions around education and particularly PhD students, is there a successful model where, say, one PhD student really goes deep into two disciplines? Or where one PI actually sort of sees it from both sides. And it could still be a collaboration, but instead of sort of this paradigm of two experts joining in this sort of ephemeral middle ground, to actually have one person sort of see both issues.
So I think that this is a great place to be because, in a few years from now, there probably will be people who are experts in both of those areas. But I think a lot of the tension is just with our educational university system. So as a person who spans many disciplines, I'm in departments that I've never taken classes in. And there's so much tension because universities are structured around departments, and departments have a lot of internal needs, and it is really in tension with cross-disciplinary work. So the whole university system, there are some great centers that have popped up. We've been doing some centers here at Davis with some success, sometimes not, because there's just so much competition and tension within departments to fulfill their needs. So I really hope that there was our previous chancellor was really trying to rethink a lot about boundaries and disciplines and how funding models worked so that we could invest in research areas. And I think Arizona State University has been the main one who's changed the paradigm and has been investing in research areas instead. But it'll be interesting to see how the evolution moves forward because there is this great tension between our traditional educational structures and the new world where the interesting questions span multiple disciplines.
I'm going to keep us on track. Last question.
So Rob Feenstra began this morning by talking about the replicability crisis. And I want to talk about a different crisis that's been occupying my attention, which is what happened on November 8th. And so the New York Times the day before said 85% probability of Donald Trump losing and Hillary Clinton winning. Now, is that social science? Is that, I understand there are computational models that were used to develop this kind of prediction? Is it simply that we just, it was a 15% chance and that's what happened? Or were the models wrong? What's going on?
And there's we're all talking about data, and I was just working with George a few days ago, and he brought up the really great point that he had all this all this data that he had paid for on internet usage, and it was riddled with errors. So he has big data, but it's not very good quality. So, we all need to be a little bit cautious and not just think that the data is the ground truth, but understand that there's flaws in collection, sampling errors, especially in these huge systems. Do you snowball sample? Do you choose nodes at random? So I think there's many interesting issues that we need to understand of how to sample, how to understand if data is really trustable or not. So he found these flaws from doing different analyses and finding unusual things. So we have to break the data down from more dimensions than we can even imagine to make sure that it actually is telling us what we think it is.
I hope to give you some answer in 3 months.
Yeah, following up on that, I think, yes, I think that's a big, and that's also maybe different to other sciences, because in the social sciences you have often real consequences on the people with your findings. And this, I like the word digital footprint much better than big data, because in agreement with other people, it's about data fusion, about other things. It doesn't have to be only the size. So I think the problem is that this digital footprint is so impressive. It is so impressive. We can see so much with it that we mistake it for the foot. And that's the problem, right? And if you hear people like the director of NSA say, yeah, we kill people based on metadata, right? And yeah, I mean, that's the ultimate trigger that you can pull. And people get parole in prison or not based on the digital footprint and so forth. It's kind of like Minority Report, or we're judging, but we're always doing that. I mean, I pay more for my car insurance than somebody else just because of my profile, my statistical profile, right? So we've been doing that for many, many decades, right? But just right now, these predictions become so impressive that we already judge and make ultimate judgment. And that's actually another thing I think where the social sciences has a particularity. And as you notice now, I'm interested in finding what makes computational social science also different from other computational sciences. Stationarity I mentioned, and this is one thing as well. I mean, in physics, if you mistake the footprint for the foot, all right. But in social sciences, oh man, that can have really scary consequences.
So we're going to take a break now. We have 15 minutes, and we will reassemble at 10:40. There's food and coffee.